Hello, I'm Tina Carbrello, Chair of the NAMS Membership Diversity and Inclusion Committee, and it's my great pleasure to announce the next installment in our NAMS webinar series. Today, we're going to hear from Professor Bill Phillip from the University of Notre Dame. We're looking forward to your presentation. Take it away, Bill.
All right, yeah, thank you, Tina, for the kind introduction and the opportunity to be here today and tell you a little bit about the little small amount I know about making membranes using phase inversion processes. And so I'll admit right out of the gate that this is an incomplete introduction to the approach, but hopefully a useful primer to get started with. Before I go ahead and start presenting the slides, I do want to mention that I make use of a lot of references, and it was just too crowded to put them all in the bottom right-hand corner. And so they're numbered in the bottom right-hand corner on the slides. And then at the end of the presentation, there's a reference page that we can appeal to understand where those references came from. And so I guess the way to get this started and motivate the desire to understand the membrane fabrication process a little bit more is that there's a lot of exciting work in developing membranes across a variety of length scales, right? So there's people that are interested in making new molecules or new materials that have exciting structures and exciting properties that could potentially benefit membrane separations. And so they're thinking about how to engineer the pore structure, create higher densities of pores or permeable domains. And they want to make membrane materials that are resilient to long-term operation in extreme environments. And so in terms of thinking about this at a length scale, I think the membrane spectrum, right, or the filtration spectrum, which you'll find on a lot of membrane manufacturers' websites, is a useful way to think about this, right? So by controlling the polymer structure, you're able to make membranes that have free volume or pore elements at the angstrom scale all the way up to membranes with free volume or pore elements up to the millimeter length scale, right? And so over that whole range, you've got a membrane operation that's able to separate molecules based off of their relative size, right? So in this instance here, you're thinking about water filtration. And so an ultrafiltration membrane can allow you to retain viral particles while allowing the solution and smaller molar mass components to go through. And reverse osmosis membranes produce potable water by retaining the dissolved ions or salts. Right. At the other length scale, people are thinking about how to develop optimized systems that get plugged into infrastructure in order to reap the benefits of these membrane separations. And in order to do that, you want to be able to design systems that maximize product recovery and purity and that are robust to the annual or diurnal variations in operating conditions. And the way I think about this at a size scale is during my graduate studies at the University of Minnesota, I had the fortunate opportunity to visit the ultrafiltration plant up at Columbia Heights. And that ultrafiltration plant is able to finish the water for the Minneapolis community and produces about 70 million gallons a day of fresh water operating at an applied pressure of about 30 to 40 psi. And to plug this into the length scale of designs, it requires a massive amount of membrane area. So to stay on theme with the units of meters, I put it in meters squared here, but I know it's on the order of about 1.7 million square feet of membrane area that are packed into these membrane modules contained within a room not much bigger than a high school basketball gymnasium, right? And so the way they do that is by taking flat sheet membranes in this case and rolling them up, right? So that you can see in this cross section how the membranes are rolled up into these spiral wound modules that at the finishing or at the end of their production are about 1 meter in length and then can get plugged into these housing units in order to build up that 1.7 million square feet of membrane area. But there's sort of a gap in the length scales between the millimeter sized pores of microfiltration or particle filtration membranes and the meter long modules that are plugged into these ultrafiltration or membrane separation processes. And that's a gap that's filled by being able to fabricate membranes. And so if we think about the goals of fabricating membranes, right, we want to take advantage of the exciting material properties that people are engineering into polymer, ceramic, and other composite materials. And so I think the Robeson plot is one way to kind of capture this in our minds. And I know that Zach Smith from MIT has an excellent webinar talking about advances in polymers for gas separations. And then we want to create thin active layers, right? So we take these materials, and when we turn them into membranes, we want thin active layers because to first order, the flux through the membrane is proportional to 1 over the thickness. And so thinner active layers will lead to higher throughputs and hopefully less membrane area needed in order to accomplish the separation. And then, as I mentioned, at the large length scale, you want these flat sheet membranes to be about 1 meter in width so that you can roll them up into spiral wound modules that contain on order of 1,000 meters squared per meter cubed in each module. And hollow fiber membranes are able to achieve even higher packing densities because the membrane itself is made up the fiber itself is made up of the membrane material. And so the outer wall or the inner wall, depending upon the orientation, can be your selective separating layer. And then you can bunch them together, kind of like pulling someone who has long hair back in a ponytail. And so you get massive surface areas per volumes. And one way that I'd like to talk in a little bit more detail about today that people have been able to accomplish this is using non-solvent induced phase separation processes, sometimes referred to as NIPS processes for short. And the first thing I'd like you to convince you of is that in terms of execution, it's a very simple process to execute. I think you can break it down broadly into 3 steps. You first want to go ahead and formulate your casting solution. So you want to pick the polymer that or material you'd like to turn into your membrane. You'll dissolve it into a solvent. And a key component of the process is plunging that solution into a non-solvent at some point in time. And so defining the thermodynamics of the system, you're going to want to select your non-solvent at the outset as well. And then you take that homogeneous casting solution and you draw it down into a thin film using a doctor blade or some other sort of coating technique. You may choose to evaporate some solvent. We'll talk about that step in a little bit. And then you plunge that cast film into the non-solvent in order to initiate the phase separation of the polymer, fix the polymer structure in place, and form your membrane. And then there may be some optional post-treatment steps. And so in order to show you just how simple it is to execute in the lab, here's an image of someone from the team making a membrane using a non-solvent induced phase separation technique. They take the casting solution and distribute it at the top of the glass slide, and then use a doctor blade to draw it down into a thin film. And in this case, he wanted to use an evaporation step, and so solvent's evaporating from this cast film. And then when you plunge it into the non-solvent bath, which is just water in this case, you see the polymer precipitate as it turns from this clear casting solution into an opaque white film. And so this process that occurs at the lab scale can get scaled up to a pilot scale. And this image here gives us a little bit of a sense of how membranes are cast using a roll-to-roll process. And so what you'll do is you'll take some sort of non-woven support, and that comes in a large roll over here, and then it gets passed through some cylinders or through some guiding cylinders until it goes underneath the doctor blade. And so here in this image, there is a doctor blade or a blade with casting solution on the other side. And so as the support rolls through this blade, a thin layer of polymer solution is being deposited on top. And then in this case, there's also a solvent evaporation period. And so in this space here, where the film is open to the atmosphere, solvent can evaporate. And then there's a non-solvent bath on the backside where the polymer is being precipitated and the membrane structure is being formed. And so here in the lab or pilot scale, this dimension here is maybe about 30 centimeters, maybe slightly larger. When you think about doing this at the actual casting scale, this dimension here will go all the way up to just over a meter. And so this is a process that can go ahead and create very large areas of membrane. And even though it's got this capability to create large areas of membrane, by modulating the formulation of the casting solution, the evaporation process, the non-solvent identity, and maybe some post-treatment, you're able to create a rich array of nanostructures or microstructures using the technique. And so along the top of this slide here, what I show is top surface, or I guess cross-sectional SCMs in the case of the RO and gas membrane, but top surface SCMs for these three here. And you can see as the average pore structure goes from small or almost a dense membrane on the left up to large pore sizes characteristic of a microfiltration membrane on the right. And these membranes were all made using variations on the non-solvent induced phase separation process. Additionally, you can manipulate the cross-sectional structure of the membranes using the process as well. And so you can make things like asymmetric membranes here on the left, where on the top surface of this membrane, which happens to be situated at the bottom left of the micrograph, you have a dense polymer film, and then the pore structure becomes graded and opens up into larger pores that provide mechanical support, but don't provide much resistance to flow in the top right. Alternatively, you can create isotropic membranes where the membrane structure has a similar characteristic pore size from the top surface of the membrane to the bottom surface, all by manipulating the non-solvent induced phase separation technique. And so in order to talk through how we might be able to generate this rich variety of nanostructures, I'll break down the individual steps. And so we'll start with formulating the casting solution and selecting the non-solvent that will be used for the process. And the place to begin understanding this is that this porous structure is created due to liquid-liquid phase separation. And so just a simple binary two-component phase diagram will help us understand a little bit about the complex issues associated with the non-solvent induced phase separation technique. And so the first thing to mention is that you need some non-ideality in order to drive this phase separation, right? Two materials that form an ideal solution will mix at all ratios. And so you need some non-ideality to drive this phase separation. And a simple way to begin contemplating that is in the case of a polymer solution using the Flory-Huggins theory. And the thing to really point out in the Flory-Huggins theory is this enthalpic repulsion between solvent and polymer, or the two components, is what drives phase separation. And so the larger this enthalpic component becomes, the more readily the material will want to phase separate. And so I'll draw your attention to this Flory-Huggins chi parameter, which can reasonably be approximated using a regular solution type theory as this prefactor times the difference in solubility parameters squared. And so this idea of difference in solubility parameters is going to become important later on, but where big differences in solubility parameters means that the two materials really don't want to be next to each other, and that's going to favor driving phase separation. In terms of the diagram on the right-hand side, where we actually have the phase diagram for a binary system, I plot the process variable here on the y-axis, right? And this process variable might be something like temperature. And so at high temperatures, where T is large, chi will be small. And in this region up here, where that process variable temperature is high, you'd have a single homogeneous liquid phase, right? And then as you reduce the temperature and the repulsion or the enthalpic contribution grows, then what will happen is you'll enter this miscibility gap, right? And so we'll talk about the red line and the dashed line, but in this miscibility gap is where we have liquid-liquid phase equilibrium. And so this red line is what defines the phase boundary. It's the binodal. And when we make measurements of cloud points of casting solutions, those cloud point measurements are establishing the binodal of the phase diagram. The spinodal, this dashed line inside of the binodal, is the limit of stability. And so this idea of a spinodal and this limit of stability will become important as we think about membranes whose structures grow either by a nucleation and growth mechanism or a spinodal decomposition. One other useful thing to just remind ourselves about these process diagrams where we have the process variable on the y-axis and the composition on the x is that as you plunge into the two-phase region, the material phase separates along tie lines, right? And so in this case, the tie lines happen to be horizontal lines. And so I form my polymer rich phase here and my polymer poor phase here that are in equilibrium with each other. And I can also use a simple lever rule to go ahead and determine how much of each phase would be formed. And so the amount of polymer pore phase that would be formed would be this length here, A, divided by the total length of the tie line. And then the amount of the polymer rich phase is just B over that total length. And these ideas translate then to the ternary phase diagram, where we think about a polymer solvent and non-solvent system. And just to remind ourselves about how these ternary phase diagrams work, each edge on the outside of the ternary phase diagram represents a binary mixture. And so that binary system that we just talked about on the prior slide, where we have polymer and solvent, would be represented by this edge of the ternary phase diagram. But we also have our solvent and non-solvent, and that binary mixture is represented here. And then you can finish off the ternary phase diagram by drawing the last edge of the triangle. And then in terms of reading these ternary phase diagrams, it's helpful to remember that the composition associated with a particular material is defined by the lines inside of the ternary phase diagram that are parallel to that point, right? And so the polymer composition is defined by these horizontal lines that run from left to right, whereas, for example, the non-solvent composition is defined by these lines that run diagonally from the bottom left to the top right. And so then you can define uniquely the composition of the phases that are formed by putting a point somewhere within the ternary phase diagram. Right. And so you can also then overlay the miscibility gap or the phase equilibria onto this ternary phase diagram to understand the compositions of the polymer rich and the polymer poor phases that are formed. One quick note is the tie lines don't need to run in any particular direction relative to the axes of the ternary phase diagram. And so here you see that they're slanted a little bit. And if I were to go ahead and put a point inside of the miscibility gap on this tie line, then you would phase split along this tie line. And if we're thinking about this in terms of the membrane formation process, this polymer rich region ends up and forms the matrix of the material, and this polymer pore region forms the pores of the material. And this placement of the relative distance of this line to this line is approximately equal to the porosity of this micrograph. So this lever rule idea persists even in the ternary phase diagram system. And so as we formulate the casting solution, it's very helpful to go ahead and think about how we might be able to define this binodal or this phase boundary by picking different materials in the casting solution. And so I'll remind you that I mentioned that this difference in solubility parameters is important for defining the miscibility gap. And so you'll note here that for polyether sulfone, the difference between the miscibility gap or between the solubility parameter of DMSO and polyether sulfone is greater than the difference in the solubility parameter between N-methylpyrrolidone and polyether sulfone. And what that ends up doing is translating to the position of the binodal on the ternary phase diagram. And so DMSO, which has a larger difference between the solubility parameter with polyether sulfone and a less favorable interaction, has a miscibility gap that requires much less non-solvent or water to be added in order to hit the cloud point. Alternatively, NMP, which is a slightly better solvent for polyether sulfone, has its binodal line or cloud point pushed further to the right, which means that the N-methylpyrrolidone is maybe better able to mediate the interactions between the polyether sulfone and water as the water is dosed into the system. And so slightly more water can be put in to the casting solution. Another thing to point out here is that the choice of the non-solvent will also affect the position of this miscibility gap. And to highlight that, I'll draw your attention to this plot in the top right corner. And so the precipitation value is just the amount of a particular non-solvent that had to be added to a casting solution in order to reach the cloud point, right? And this study examined that as a function of temperature. But I'll point out that about 15 grams or 15% of the casting solution needed to be non-solvent or water in order to hit the cloud point for NMP and polyether sulfone. Alternatively, if I have something like methanol, which has a little bit of a less unfavorable interaction with the polyether sulfone, you need to add in a significant amount of non-solvent in order to hit that cloud point or to establish the binodal, right? So here it's about 45 grams, or I would need about 45% of the casting solution, the solution to be methanol before I hit that cloud point. And so that binodal line for a methanol NMP polyether sulfone system is shifted all the way over here to the right relative to what you see for a methanol water polyether sulfone system. And so as you formulate the casting solution, the selection of solvent and non-solvent can really be guided to first order quite well using these solubility parameters, which are documented at great length within the literature. And so that you're able to go ahead and shape the miscibility gap through these selections. There's one other thing to mention about this ternary phase diagram and its relationship to the dynamics or the system that we're examining, and that's that the addition of solvent can lower the glass transition temperature of the polymer. And so I'll just remind you that if the ambient temperature is below the glass transition temperature, the polymer is glassy and it behaves like a solid. And if the ambient temperature is above the glass transition temperature, the polymer is rubbery and can flow like a liquid, right? And so for pure polyether sulfone, the glass transition temperature is about 498 degree Kelvin. And so at room temperature, it's clearly established as a glass and behaves like a solid. But as you begin to put more solvent into the system, you see the glass transition temperature fall. And as we go or follow this line for NMP, once I get to about 65% polyether sulfone dissolved in NMP, so only about 35% NMP in the solution, the glass transition temperature is below room temperature, right? And so if we go ahead and assume that membranes are cast at room temperature or 298 degree Kelvin, then these materials or these formulations where I have, 35% or more NMP in the casting solution will be rubbery and can flow like a liquid, whereas these compositions here will be glassy and won't be able to flow. And so at this point, this crossover at about 70% by weight PES adds an additional line onto the ternary phase diagram that defines where the system will vitrify or turn into a glass. And so as the phase separation process is occurring, once the material turns into a glass, it's too difficult or its mobility is too low for it to rearrange and its structure is fixed in place. And so then we've got, I think, 4 regions on this phase diagram that we can think about. So outside of the miscibility gap, we have one liquid phase, as long as there is about more than 70%, less than 70% polyether sulfone in the solution, and one glass phase if there's more than 70% polyether sulfone. And then inside of the miscibility gap, depending upon where we are, the tie line may draw me to a point where the polymer-rich phase remains to be a liquid and can flow like a rubbery polymer, or it may drive me up into the glassy region where the polymer will go ahead and vitrify and lock itself into place. And so this interplay between the thermodynamics and dynamics can be captured with this vitrification line, and it's important in terms of the structures that can be formed using this non-solvent-induced phase separation technique. And so with that sort of discussion of the casting solution and the non-solvent, I'll mention that as first approximations, the casting solutions have about 15 to 20% polymer dissolved in a polar water miscible solvent, or potentially a mixture of solvents. And then the non-solvent is often water. You want the rapid precipitation afforded by the large difference in solubility parameters, or you want this binodal curve to be relatively close to this edge of the ternary phase diagram. You can blend some solvent in to slow the precipitation. We'll show an example of that in a couple of slides. And so with that little discussion of the formulation of the casting solution, we'll go ahead and imagine that we've cast our solution into a thin film using a doctor blade. And for the time being, we won't discuss a solvent evaporation step, and we'll plunge that material directly into the non-solvent bath. And so one thing that happens as you plunge that material into the non-solvent bath is you have this exchange of solvent and non-solvent. And so you begin to take some trajectory into the middle of the ternary phase diagram from the left edge where your casting solution was. And the angle of this trajectory depends on a lot of things, but in this case, imagine we go along this trajectory. And as you continue along that trajectory, then you can plunge or go through the cloud point or the binodal curve. And depending upon the relative rates of solvent and non-solvent exchange versus phase separation, two things can happen. If phase separation is rapid relative to the solvent exchange, you may phase separate and then begin to grow your membrane nanostructure or microstructure through a nucleation and growth mechanism, but where it phase separates and then these structures ripen over time. Alternatively, if the non-solvent-solvent exchange is much faster than the phase separation, then you can plunge down into the spinodal region and have a material phase separate through a spinodal decomposition. And the choice or the path that the material takes is largely dependent on being able to quantify the rates of solvent and non-solvent exchange, the rate of phase separation, as well as the rate of polymer vitrification. And so it kind of highlights as we move towards this non-equilibrium process and just the complexity that can emerge. And so I don't have as many good descriptions about the dynamics of the system as the thermodynamics, because I think that this is an area where there's a lot of opportunity for understanding. But I will talk a little bit about some excellent work that's been done to maybe begin to understand what happens during this solvent non-solvent exchange and how that interplays with the polymer physics and thermodynamics. And so let's imagine here on the right-hand side that this is our casting solution, and we plunge it into our non-solvent bath. And so then we have solvent non-solvent exchange, and this drives a diffusion front of non-solvent into the casting solution. Right, so that's that first arrow that we saw on the prior slide. And once that arrow goes through the binodal or through the spinodal line, and you have enough non-solvent present to cause the phase separation, then there's a phase separation front that lags behind the diffusion front. And as more solvent and non-solvent exchange and the non-solvent concentration becomes even higher, then you have a gelification or a gelation or vitrification front grow in, right? And so the diffusion front precedes the phase separation front, which precedes the vitrification front. And they all grow through the film. And I use this diagram, or I use this description, because Tony McHugh, when he was at the University of Illinois, did some really nice work using microscopy in order to isolate these different regimes. And so on the left-hand side, you see a cross-sectional micrograph where here, this sort of fuzzy region of speckled gray is the vitrification front that's moving through the cast polymer solution. This leading edge of the very dark black region here is associated with the phase separation front, and then these fringes are due to the interaction between solvent and non-solvent, and so this leading fringe represents the diffusion front of solvent-non-solvent exchange. And so they're able to make these measurements for a variety of different materials, and then can correlate how these lengths grow as a function of time in order to maybe understand a little bit about the dynamics associated with the phase separation process. And so here I'll begin by showing you the distance squared on the y-axis, and it's a distance squared sort of leading into this idea that these are diffusion controlled processes at short time scales. And so this allows us to identify diffusion controlled behavior by plotting it as a length squared versus time. And so here there's two length scales plotted for two different polymer solvent systems. And so there's the length scale associated with the diffusion front, and that's plotted for a polyether sulfone in NMP and a polyether sulfone in DMSO. And you'll remember that NMP is a slightly better solvent for polyether sulfone than DMSO. And the difference in the growth rate of their diffusion front isn't that significant. However, they also plot the propagation of the vitrification or gelation front on this diagram. And you see that for NMP, the better solvent, it takes more time for the system to go ahead and begin to gel or vitrify due to the solvent quality helping to plasticize the polyether sulfone. Alternatively, the DMSO, its gelation or vitrification front grows at a much more rapid rate. And I'll just put this up here to highlight the connection between the ternary phase diagrams that we discussed previously and then the dynamics of the system, right? And so, you know, in Fick's law, the concentration gradient is a proxy for the gradient in the chemical potential. And on these ternary phase diagrams, the distance between 2 points is sort of a proxy for the chemical potential or the driving force. And so here you see that you're very close to the phase boundary for DMSO, and so you have these more rapid growth processes occurring. So the other thing that you can do that can begin to plug in the non-solvent induced phase separation technique with the microstructure, the membrane structures that form, is blend in a little bit of solvent into your non-solvent. And so once again, we're plotting a length squared on the y-axis and a time on the x-axis, and the diffusion front of solvent-non-solvent exchange for these two materials is relatively similar, but the addition of the solvent to the non-solvent delays the onset or the growth of the vitrification front for the mixed non-solvent system. And so here you see the mixed non-solvent system grows in slowly, whereas just pure DI water used as the non-solvent has a gelation front that grows quite rapidly. And this is nice because you can connect this with some experimental measurements. And so in this case, it's polyether sulfone membranes, and N-methylpyrrolidone is used as the solvent, but the non-solvent bath was either 0% NMP or pure DI water, 20% NMP, or 40% NMP. And as I increase the amount of NMP in the non-solvent bath, right, and have a slower penetration or slower growth of this vitrification front, I give the polymer structure, the phase separated structure, more time to grow in size. And so the characteristic size of the pores that you observe as you move from left to right increases due to the inclusion of this non-solvent, or sorry, the solvent in the non-solvent bath, and that delaying the growth of the vitrification front. You can also manipulate the growth rate of these fronts using the concentration of polymer in the casting solution. And so in this instance, the velocity of that front or the slope of that front motion, right? So the meters squared over minute is plotted as a function of the concentration of polymer in the casting solution. And so the fusion front motion is the motion of the solvent-non-solvent exchange, and this gel front is the motion of the vitrification front. And in both instances, you see that as the polymer concentration increases, that these velocities go down, likely as a result of the fact that the mobility of the polymer is reduced as its concentration is increased, and this leads to slower propagations of the front. Kind of interestingly, this slower propagation of the front leads to smaller pore sizes. And so the thing you should look at here is this first column of the matrix, where a 20% polyether sulfone is in the casting solution is plotted at the top, and 25% polyether sulfone in the casting solution is plotted at the bottom. And you see that as we go from top to bottom, the characteristic pore size becomes smaller. And so it's not as straightforward as saying that slower vitrification fronts will lead to larger polymer structures, because this slower vitrification front is a result of the polymer dynamics being slower itself, and so they can't grow as rapidly. Though you do see that as you continue to move with more solvent in the non-solvent, you do ripen the structure and end up with larger pore sizes. And so this speaks to maybe a really area of open opportunity in terms of understanding the non-solvent induced phase separation technique, is this non-equilibrium processing of the material. And one large outstanding issue that hasn't been addressed in great detail or understood in great detail is the formation of macrovoids. And so I'll show you two micrographs, one with macrovoids on the left, these large finger-like structures, and then another on the right with this sort of spongy-like structure. Both materials were cast from the same weight percent of polysulfone in solvent. The only difference between the two of them was that in this case, the non-solvent bath was a DI water that the film was plunged into, and in this case, it was a 100% relative humidity atmosphere. And so thermodynamically, these two non-solvents are identical. The activity of water is 1 in both cases, but the lower density of the vapor slows non-solvent intrusion. And so this is consistent with one of the ideas that people have about the idea of macrovoid formation, is that it's associated with the rapid intrusion of non-solvent into the film. And if you're able to slow that non-solvent intrusion, you'll end up with this more spongy structure without large macrovoids forming. Using their technique, the McHugh group did some nice characterization of this. And the thing that they noted was that when you had rapid non-solvent solvent exchange, the polymer non-solvent interface didn't move during the whole process, whereas if I had slower exchange, that polymer non-solvent interface would have an opportunity to move down slightly. And so this film bath interface moves when there's slow solvent non-solvent exchange. These did not have macrovoids, and these membranes did have macrovoids. And so we'll have a brief discussion of what happens when we now include an evaporation step. And the way I just want to think about the evaporation step is in two limits. If I have slow mass transfer in the vapor phase, or if I have rapid mass transfer in the vapor phase. And so I've turned the polymer film vertical here, just so that the concentration of polymer in the casting solution can be represented by this orange line here. And if I have slow mass transfer in the vapor, then the composition within the casting solution can remain well mixed. And as I evaporate solvent off, the polymer concentration increases uniformly across the membrane or the cast film thickness, which would be consistent with just moving the whole film composition along this edge of the ternary phase diagram, right? And if I were trying to make a dense polymer film for some preliminary materials testing of a gas separation membrane, this might be what I choose to do, because I take all of the solvent off. I have a uniform dense film of my polymer. It's above the vitrification line, and so it's formed a nice solid polymer film. Commercially, or in the spirit of trying to create asymmetric membranes with a very thin active layer, this rapid mass transfer in the vapor is likely more appealing, because this means that you're able to go ahead and remove solvent locally very quickly from the film-air interface, which means that the polymer composition increases in this region and then decays back to the original casting solution composition on the surface or the glass slide that the material is cast on. And so now, across the film thickness, I have different trajectories that the bottom, middle, and top of the film can take through the ternary phase diagram. And I'll just point out that this top portion, by moving above the vitrification line, you can create thin films of dense polymer supported by porous structures underneath. Right. It should also be noted that this is often achieved using a mixed solvent system, so a solvent that has a high volatility like THF or acetone mixed with a solvent that has low volatility like NMP or DMSO. And just to reiterate the fact that this solvent-non-solvent exchange is determined by the initial point, or the trajectory of the solvent-non-solvent exchange is determined by the initial condition of the film. I'll point out that when you do use this rapid mass transfer in the vapor and are able to evaporate material off locally, this is how you create those graded structures, where I have a dense polymer film in the bottom left-hand corner that grows in average pore size as I move to the top right corner, because of the different position these materials take through the phase diagram. And this is just a higher resolution SEM micrograph of this region of the polymer film, and you see that it is in fact dense and something that can execute a gas separation where you're trying to resolve molecules with fractions of angstroms difference in size. And so hopefully this quick primer convinces you that the NIPS process is relatively simple in execution. It's dissolving a polymer in solution, drawing it down into a film, and then plunging it into a non-solvent bath. But I think it's incredibly complex in design, and it's still a little bit more art than science in terms of understanding the nanostructure, the microstructure that evolves. And I think that there's a lot of opportunity to continue to advance membrane science by understanding how to control this process more effectively. I think I'll finish with a quick discussion of maybe some areas where I think that this non-solvent induced phase separation technique can be advanced further, right, and really help us bridge from molecules and materials up to systems and infrastructures by creating useful devices. And so the first thing that I'll mention is I think that there is growing opportunity to expand pore wall functionality. Those polymer films that I was discussing previously, after they're cast, they're often surface treatments that are used to make the membrane more hydrophilic and hopefully resist the deleterious effects of fouling. And using some new materials, like for example, amphiphilic copolymers, you can blend those amphiphilic copolymers into the casting solution of your membrane so that a functional handle can remain along the pore walls, right? So these amphiphilic copolymers have one component that likes to bury itself inside the matrix of your polymer material, and another component that likes to poke its head out into the pore wall. And this might provide for more ready functionalization of the membranes post-fabrication, right? And so you can go ahead and you can look at anti-fouling surfaces, or you can look at adsorptive membranes. I know that Professor Christine has a very nice webinar on separating radioisotopes using membranes and the opportunity for radiomedicine or impact in radiomedicine of membranes. these membranes can also be responsive in a variety of other things. And so I think this addition of chemistry on top of structure is a real opportunity. Sustainability is always on the forefront of our minds now, and I think that that's true for membrane processing as well. I believe that the European Union is phasing out some of the solvents that are commonly used in order to make membranes through the phase separation process, and then the fate of the polymers the polymer membranes that are expired, or what you do with these membranes after they've met their end of life, is also of a concern. And so there's some exciting work to try and address these ideas. I think Isabel Escobar has a beautiful review, and Wiebe de Vos has a really interesting idea where you can go ahead and dissolve polyelectrolytes in an aqueous casting solution, and by manipulating pH or other aspects, ionic strength, for example, you can go ahead and do an all aqueous phase separation based process. New materials are always coming out, and I think that they have an opportunity to go ahead and allow us to have better control over the pore structure. And so I just highlight this one example of the traditional structure that results from these phase separation techniques. While we have great control over the average pore size that's formed, you still do end up with a distribution of pore sizes. And emerging materials like block copolymers, lyotropic liquid crystals, metal organic frameworks, they have the ability to create membranes that have pore sizes that are really well defined, and that there's still a high density of these pores. And this might open opportunities for more refined filtrations. The second to last thing I'll mention is that I think this phase separation technique can be merged with additive manufacturing in order to create structures with organization across multiple length scales. And so if you think about going and creating adsorptive membranes, you could imagine 3D printing your casting solution in a humid environment. And so the 3D printing is allowing you to control the micro scale structure, where we have this wood pile structure generated by the printing algorithm. But then because this casting solution is being printed in that humid environment, you go through the phase separation process within the filaments. And so then you have this nanostructure built into the filaments that has a high surface area per volume and may be useful as a high capacity sorbent or as a support for catalyst. And that's one potential extension of the phase separation technique. People are also looking at using phase separation techniques to create liquid droplets for drug delivery. And then I think just to speak to the complexity of the system, I think there's emerging opportunities in refined computation and data-driven discovery. And so there's nice models at the molecular scale using particle dynamics. There's nice models at the continuum length scale using traditional fixed law type approaches with your transport equations. But bridging those length scales is very difficult. And there's emerging phase field modeling techniques that begin to allow us as researchers to bridge from that macromolecular length scale up to the microstructure, the membrane length scale. And as these techniques are developed, we can begin to understand the dynamics of the phase separation process even more, hopefully providing us with improved control over the ultimate structure of the materials that form. And so thank you for your attention. I'll just leave these references up because a lot of the graphics and the information that was provided comes from these references, and they're invaluable in terms of understanding the process. And so thank you.